The following program is brought to you by Caltech.
Good evening. My name is Ravi Ravichandran, the director of the Graduate Aerospace Laboratories here at Caltech. I would like to welcome you to tonight's Watson lecture. Before I introduce our speaker today, I want to mention the next Watson lecture, which is on April 17th, and will be given by Professor Brian Wernicke of the Geological and Planetary Sciences Division. And his lecture is titled, The Ancient California River and How It Carved Grand Canyon in the Age of T-Rex, which should be very interesting. Our speaker this evening is R.S.J. Rosakis, the Theodore von Karman Professor of Aeronautics and Mechanical Engineering and the chair of the Division of Engineering and Applied Science. Professor Rosakis was born in Athens, Greece, and received his bachelor's and master's degrees in engineering science from Oxford University. He then went on to receive his master's and PhD degrees in engineering from Brown University. He joined Caltech as an assistant professor in 1982 and was named the Theodore von Karman Professor in 2004. He served as the director of the Graduate Aerospace Laboratories prior to his current position. In 2005, he was a distinguished visiting professor at the École Normale Supérieure in Paris, and in 2007, he was the Astor Distinguished Visiting Professor in Oxford University. Professor Rosakis' research is focused on studying how materials fail over a wide range of length and time scales, and tonight's lecture fits that theme. A world leader in his research field and a superb experimentalist, he has made a number of pioneering discoveries, and he will share some of them with us today. He is the author of more than 250 papers and 8 patents. He has received numerous awards and honors, which include a NSF Presidential Young Investigator Award, the Rudolph Kingslake Medal and Prize from SPIE, and the William Murray Medal from the Society for Experimental Mechanics. An awe-inspiring teacher in the classroom, Professor Rosakis is the recipient of an Excellence in Teaching Award from the Caltech Graduate Student Council. He is an exemplary mentor. Many of his students have gone on to excel in research and teaching around the world. Ladies and gentlemen, please join me in welcoming today's Watson lecturer, a man I am honored to call my friend and colleague, Professor R.S. Rosakis.
Thank you very much, Ravi. It's a great pleasure to be here. It's a great pleasure to recognize many familiar faces, many of my students, my colleagues, my friends, and even some of my neighbors. So today, my purpose is to amuse you and by sharing with you the curious and amazing story of intersonic of super shear earthquakes. Now, what you see in this slide is really an outline of my talk. So let me start with the left picture. What I would like to do is start by giving you a tutorial about earthquakes, basically introduce the terminology, tell you about faults, tell you about ruptures that are hosted by faults, and the effect of ruptures in the form of seismic waves, and basically explain the reason that the Earth shakes. Then I would actually describe some historic earthquakes, historic and very catastrophic earthquakes, like the 1906 San Francisco earthquake, and then go to the lab and spend most of my time in the lab producing or explaining to you how we produce surrogate earthquakes in the aeronautics labs at Caltech. Now, of course, the reason that we do that is because we, under controlled and safe laboratory environments, we can study the properties of earthquakes, and we can do that at will, unlike what we can do on the Earth's crust, where we cannot generate earthquakes when we want to study them. After that, I will say a few words regarding seismic hazard, and finally, I will shake a building or two for your pleasure. So let me start with my research group. I would like to introduce my research colleagues from the Division of Engineering and from the Division of Geology and Planetary Sciences. This is a very interdisciplinary research group, and we are very proud at Caltech to always work in the boundaries between disciplines. In this case, the discipline is geophysics and engineering. Professor Hiro Kanamori was the person with whom I started working on this subject about 8 years ago. Former director of the Seismolab and a card-carrying seismologist. Professor Nadia Lapusta, a theoretical mechanician, is a professor of mechanical engineering and geology and planetary sciences. Professor Swaminathan Krishnan is a card-carrying civil engineer who is a professor of civil engineering and geology and planetary sciences. And of course, the two people that have done most of the work, Harsha Bhatt and Mike Mello. Harsha is a postdoctoral fellow at the Graduate Aerospace Laboratories. He is a theoretician, slowly becoming an experimentalist. And Mike Mello is an experimentalist, slowly becoming a theoretician. So I promised a tutorial. So let me start with some definitions. I want to actually first tell you what is a crustal earthquake. So according to a formal definition, an earthquake is a term used to describe both the sudden slip on a fault and the resulting ground shaking and radiated seismic energy caused by slip. And usually, when we think about earthquakes, we think about plots like this of ground acceleration versus time in seconds here. This is what is usually recorded. Now, of course, earthquakes are generated by frictional shear ruptures, spontaneous frictional shear ruptures that occur along weak planes, and the emphasis here is on the weak plane, or faults in the Earth's crust. Here is a very big weak plane that hosts earthquakes. Ruptures or huge cracks propagate and unzip these planes, like the one that you see here from an area view in Central California, and they produce the ground shaking. Now, a few words about the geometry here. So this is a weak plane separating two plates of the Earth's crust. Those are crushing against each other, and they shear, they move in the directions that you see. Now, the plane actually extends down vertically for many kilometers, and it is there that the earthquakes happen. The two plates that are moving against each other have a very small speed of only 20 millimeters per year. 20 millimeters is this is nothing. So in a year, they just move 20 millimeters in average. But what happens is that as they move, there are sudden events that take place. And let me show you graphically one of these events. Here are the plates, and perhaps you can imagine the fault somewhere in the middle here. And the movie will show these plates moving extremely slowly at 20 millimeters per year, and suddenly you see things flare up here, and there is an earthquake. And there is slip. And this slip here is not only 20 millimeters, it's many meters. It could be up to 10 meters. So, and that happens periodically, and in the course of things. And what I'm interested is not in the slow motion and the periodicity. I'm interested in the event itself. I'm interested in what happens when one of these lips takes place and radiated energy escapes. So the next thing that I would like to tell you about is rapture speed. Again, a formal definition first. Rapture is the propagation of slip along that frictional or incoherent weak interface, the fault, as opposed to a coherent interface that has strength and toughness. A glued interface would be a coherent interface. Now, in an analogy, you can think of this as a very fast unzipping action of your sweater. So the speed of the motion of the zipper is the rapture speed, and it happens along a plane of your sweater. Let me use an animation that was produced by one of our graduates from civil engineering, Dr. Brad Agard, who is now with the US Geological Survey, to explain this. What you see here is a section, a box that is describing the Earth's crust. And here you see one of these weak planes that actually extends down many kilometers. And there is an observer above the Earth that is going to look at the zipper moving towards the point of observation in a second. So let me click on this movie. And what you see is the weak plane here, and something is coming very fast. This is 15 kilometers, 10 kilometers, 2 kilometers, very fast towards the observer, and it's shaking the Earth. Really, this is exactly what happens. This is the strange unzipping action that has to do with shear motion, like this along the plane. And it's not a normal engineering crack that opens up this way. The speed of this is the rapture speed. Please remember this, because this is a very fast speed. There are other speeds that I'm going to speak to you about. So, next thing I would like to discuss is what are seismic waves and why we're afraid so much of ground motion. So let me put it in context in Los Angeles, and surely you will be afraid of what you're going to see here. So here is Los Angeles. This is the Salton Sea, close to the Mexican border, and there is a line here, which is the weak plain, part of the San Andreas Fault, that actually goes back in the back of the mountains. Pasadena is somewhere here. And it goes up towards San Francisco. And I'm going to actually generate an earthquake that runs here, unzips, and sends waves towards Los Angeles. And those are going to be observed here. This is downtown, Rosemead, Pasadena, Whittier, and so on, the Dodger Stadium. And of course, this was not done by me. This was done by the SKEC Shakeout Simulation Workshop, and it's actually a non-movie. I'm going to use this to explain the nature of waves. So as I'm running this, you're going to see something happen at the beginning here. There are blue waves coming out. Those are the pressure waves. There are yellow waves coming out. Those are the shear waves. And they are actually red waves coming out. Those are the Rayleigh waves, and I'll explain each of them. What I would like you to note is that the tip of the rapture of the zipper moves with speeds very close to the Rayleigh wave, very close to the red. So actually, what are the pressure waves? The pressure waves are called sonic waves, and they are such that the motion of the particles is parallel to the motion of the wave, like this. Whereas the shear waves, and they go very fast with 5 kilometers per second. They have reached Los Angeles now, how many seconds? In 52 seconds. This is the blue. The yellow is coming afterwards. The yellow are waves that move like this, perpendicular to the motion of the wave. And the Rayleigh waves are the most catastrophic ones. The yellow are coming, you see actually the first waves have not shaken Los Angeles too much. The yellow ones are moving it in plane. And the Rayleigh waves are the ones like the waves in the ocean. They go like this. And they are the slower ones. They go with 3 kilometers per second. And as you can see now, the Rapture has gone in the back. But these waves, depending on the geology here, they have followed specific paths into the Los Angeles basin. So now you know what waves are and what to expect first. The pressure waves first, the shear waves second, the Rayleigh waves third. The Rapture speed actually is partially responsible, it's intimately responsible to ground shaking. The bigger the speed of this Rapture that was moving, the zipper speed, the more intense the ground shaking. And I'm going to say something about this. The question is, how big can the Rapture speed be? As a matter of fact, this talk is exactly about this. How big can the Rapture speed be? So let me go and look at the literature. And of course, there is a famous article by Professor Kanamori and one of his students in 204 that discusses the Rapture speeds. And it says that within the resolution of the inversion process, the majority of field evidence suggests Rapture speeds and zipper speeds between 80% and 100% of the Rayleigh waves, of these ones, the red ones. Those are called Subrayleigh or subshear ruptures. So in these ruptures, this is the type of shaking that we see. First of all, the P waves come, the blue ones, if you remember. There is very little shaking. The S come, there is an S wave train, and then the big one is associated with the arrival of the Rapture itself and the red, the Rayleigh waves. Now, what I'm going to do in this small animation is I'm going to forget about the P waves and the other ones and just tell you what happens if a source, which is the zipper moving along my fault line, emits S waves, and it moves with a certain speed. Actually, let me go back. So here is the source moving. It's emitting these S waves. It, of course, emits other waves as well, but I'm only showing you the S waves. And there is an observer, and the observer is going to be hit by multiple wave hits. As you can see, there is bunching up in the right direction because of the Doppler effect and the fact that things are moving in this direction. So actually, the first S wave hits, and there is a wave train that is felt here because of the multiple hits. Now, the faster this goes, the smaller this time distance becomes. It's squeezed. And let me show you the extreme of this. Suppose now, and at this point is only a suppose, that the Rapture front could move faster than the S waves. You know, the case that I showed you before, I had a Rapture front that moved slower than the S waves. And the question is, how would a super shear or intersonic Rapture look? What do I mean by super shear or intersonic? I mean a Rapture speed which is less than the speed of the P waves, but more than the speed of the S waves, intersonic. That's the reason for the name. So in this particular case, let me show you what the animation will show. Again, I'm concentrating only in the S waves. This is moving faster now than the ability of the medium, the crustal rock, to transmit waves. And look what happens to the observer. It's hit by a bus. And it's hit basically by something which is called a shock wave. The congruence of wave hits gives rise to what is called a Mach front. And this is characteristic of many supersonic or super shear events of our everyday life. And I'm going to show you one in a second. So really, if you are measuring the ground acceleration, you'll get the P waves coming fast because you are moving less than the P waves. And then very shortly after that, you're going to start the big ground shaking because you have been hit by this. So this looks different than the previous record. Now, let me tell you how a Mach front sounds. After all, I am a professor of aeronautics. And so actually, imagine a supersonic aircraft going faster than the P wave speed in air. Air has only one wave speed, unlike rock that has 3 that I showed you. So shockwave, which is associated by the source, in this case the aircraft, moving above your head. Shockwave here because the sudden change of pressure, the jump in pressure in the vicinity of the shockwave allowed the formation of droplets. This was a very humid day that actually outlined the shockwave. That would not happen in California. So, in this example from aeronautics, Mach fronts, these are the Mach fronts. Remember, the fronts that are created by the fact that you are going faster than the ability to transmit information are audible. We can hear them. They are jumps in pressure. While in the case of earthquakes, they are not jumps in pressure because we are only exceeding, in my example, the shear wave speed. So they are jumps in shear. So we want to study here what Mach fronts do, what is the effect of shear Mach fronts generated by super-shear earthquakes. Now, how do I know that these things ever exist? Actually, about 8 years ago when we started the study, nobody knew that they really existed. And there was indirect evidence, and there was only one person here, Ralph Fazzuletta, who actually published a paper in 1984 that claimed that something like this happened in 1979, in the 1979 Imperial Valley earthquake. That was a 6.5. Now, that was, for many years, was not widely accepted information, and it was only recently, with the work that we started with Kanamori in the laboratory, that we were able to actually show that such things exist and they can be reproduced in the laboratory at will under certain conditions, and that's what I'm going to be telling you. Since then, there have been a number of cases that we have gone back and reanalyzed and with our co-workers, like the 1999 catastrophic Izmit earthquake in Turkey that killed thousands of people, and even the 1906 San Francisco earthquake, and most notably the Kunlun-shan earthquake in Tibet, which featured something even more important. It featured a transition from a normal earthquake to a super shear earthquake. It is exactly for this reason that I have divided these earthquakes to 2 parts, my personal favorites, which are the really catastrophic ones. They're above 7.4, but they all actually featured something what is called the transition from Subrayleigh to super shear. And I will tell you a few things about those. Let me start with Izmit, 1999. Again, now you know about faults. This is a fault line. So actually, this is the part of the North Anatolian fault. And let me orient you. Istanbul is somewhere here. Anatolia, looking towards Iran, is here. And the Black Sea is above you. And here is the fault trace. And there is the hypocenter. And there was, in this particular event, the rupture became bilateral, meaning it spread to the right and left. So there was rupture to the right, rupture to the left, and there were 2 stations that were very fortuitously placed to the right and left, almost equidistant. And this is what they recorded. Now, in a paper with a French seismologist, Michel Bouchon, we looked at the speeds, and actually, the left part propagated in a classical Subrayleigh fashion at a speed very close to the Rayleigh wave speed, while the right part propagated in a super shear fashion in a speed that was actually very close to a magic number here, square root of 2 times the shear wave speed. So more than 1.4 times the shear wave speed, and it was super shear. And of course, now, after our discussion, you can see the differences between the record to the left and the record to the right. Remember, the record to the left has the P waves, the S waves, the other waves, and so on. This one has P waves and immediate ground shaking, because almost immediately before the S waves come, the rupture is close to the station. In China, there was another very big earthquake, not catastrophic at all because there is nothing built in Tibet, but it was very interesting from the mechanics point of view. Here is the fault trace. It's an almost vertically dipping fault. And what I would like to say here is that it started for the first 100 kilometers as Subrayleigh. It propagated with 3.3 kilometers per second only. And then the unzipping became very fast, and it actually jumped almost to the pressure wave speed, 6 kilometers per second. And what is interesting here, look at the offset, the sliding. The sliding was up to 8 meters. So this is really fantastic offset that would happen in a few seconds. The third one, the one that I'm going to spend a little bit of time later with, is the Denali Alaska one. The red fault trace there shows exactly the location of the fault. The star is the hypocenter. It started somewhere there and propagated for the first 72 kilometers at Subrayleigh, and then transitioned to super shear. And we were very lucky because there was a station there, a seismic station, about 3 kilometers from the red line, which is called the Pump Tent Station, and recorded very interesting signals. So it's time to take you to the laboratory. Knowing all these things and knowing all of these eventualities, we actually, Professor Kanamori and I and our co-workers, decided to actually try and see whether we can reproduce some of these events in the laboratory. You see basically the idea. What we did is we took 2 pieces of polymer representing the crustal rock, and we held them together under frictional contact. So they are compressed and they held here under friction. There is no glue. So in this setup, the rock is replaced by the photoelastic polymer. The fault is replaced by the inclined contact interface. The tectonic stress, the forces that basically compress and shear, are replaced by this load and the fact that the angle changes here at will. We can actually do experiments at different angles and different loads. And then we have to worry about the hypocenter. So let me tell you about the hypocenter. So here is how it looks in the laboratory, 2 pieces of polymer. This is the inclined interface. The load is applied in this press. And in order to start the earthquake, and then photograph it with a high-speed camera as it spreads in real time, we drilled a very small hole, the diameter of a human hair. And we put a nickel wire inside it and held it with 2 electrodes to the right and left. And you see, actually, the electrodes here. And discharged a whole capacitor bank across it, producing a mini plasma explosion, basically producing a counter pressure, countering the static pressure to allow the earthquakes to start rupturing to the right and left. So we created the runaway earthquakes to the right and left, and we mimic that way the hypocenter. As this was happening, we placed the specimen, this part, inside an optical setup called the photoelastic setup that allows you to visualize the shear stresses in the specimen, and actually photographed it with a high-speed camera. This high-speed camera is very fast. It's capable of 100 million frames per second, but we used it only with 1 million frames per second in this particular experiment. This is how the setup looks. I am showing this because my student, Mike Mello, has really insisted that I show the intricate setup. These are the high-speed cameras. This is the specimen here. You see some of the light going through. I'm not going to go into the great details. There is a lot of science and engineering going to these measurements. So I would like to share with you some of the results immediately in a visual sense. So here is the specimen, the hypocenter. The ruptures are going to go to the right and left. This is the fault. Imagine now that you are on a satellite looking down on California, and San Francisco is here, and Los Angeles is here. This is the hypocenter. And the small explosion happens, and the earthquake starts propagating to the right and left bilaterally, emitting these waves. And here is your shear wave. So this is the S wave, and this is taken at 30 microseconds. A microsecond is a millionth of a second after the explosion happened here. So this is propagating with very high speeds, and I'm going to show you a movie in a second. And those patterns are stresses associated with the crack that is spreading to the right and left. And now the rupture, the zipper is here, the rupture tip, and it's moving at very high speeds. So the way that we started this with Professor Kanamori, that goes back to 8 years ago, that part, is we had a bet where actually I was betting that immediately we're going to have super shear because I wanted it to happen. And he was betting against that because he had just written the paper. And so we hired a common graduate student, Xiao Lu, whom we worked together so that we had equal input. And he started this experiment, and that was the first picture he got. And I panicked. I said, there is no super shear. This is very classical. This is exactly what the textbook says. So to make a long story short, I was pressing for extreme conditions. And what are the extreme conditions? You increase the angle of inclination. You increase the driving force. You increase the pressure. So actually, this angle is 25 degrees. The pressure is 70 bar of 7 MPa. And if you now increase the pressure to almost double, with the same angle, you see a totally different picture. And I was able to breathe because I could see the shock waves. And here is the same S wave trace, and something is happening in front of the rupture tip. There is another zipper in front of the zipper. Actually, yes. So something is moving faster than the S waves, and it makes a Mach cone like the supersonic airplane. And this is the shear shock wave. Again, the optical technique was chosen to be able to be sensitive to jumps in shear stress. So that's what you see here. Now, of course, when this started, it opened up a Pandora's box. And of course, when you start playing games with it, the next game we played is, okay, let's go half the pressure. What happens if we have the same angle of inclination, and we have, instead of 7 or 13 MPa, we go to 10 MPa. And here you see, actually, something which is interesting. This is the same experiment, 30 microseconds and 38 microseconds after the rupture has started. In the beginning, it starts exactly as the previous one was, the classical one. It spreads with Subrayleigh speeds. There is the zipper here. But then, at that point, something is happening in the front. And the mother rupture here produces a daughter rupture And this is the daughter rupture that starts propagating with shock waves. So the mother can do what the daughter could not do. Actually, the daughter could do what the mother could not do. I got it all wrong. And actually, if you look at the theory, and I am going to shield you, promise, from the theory, you will see that there is a forbidden speed for cracks and ruptures that one can calculate, and Professor Lapusta can tell you all about that, that actually the mother rupture cannot exceed the speed limit, but she can generate a daughter that can. And that is what is happening here. The interesting thing is that there is a transition length, that there are conditions at which the rupture start, becomes Subrayleigh first, and then transitions after a length. And in this experiment, it was only 20 millimeters. In China, it was 100 kilometers. And of course, there's an issue of scaling up. But that's what we do best, multi-scale mechanics. Before I actually go to the scaling up and to other issues, let me show you a movie. Here is your specimen subjected to compression and shear because we are pushing in the inclined interface. There is the explosion. And as I continue, you see the shear wave expanding. And then suddenly, you see the formation of the daughter and the shock waves. The mother is still here. There is a transition length. And one can actually build very nice theories about this and show that the transition length is inversely proportional to the load or the tectonic pressure to the power 3/2. So basically, the bigger the tectonic load, the smaller the transition length. Now, there are many questions that arise from this, but let me show you, first of all, how the speeds look. So remember, this is a plot of the speeds of the two zippers. There is one zipper to the right, one zipper to the left. Initially, the speed is below the Rayleigh wave speed, as it should be in a classical rupture. Here it is. And the other side. And then suddenly it jumps. But it's not the same one that jumps. It is the daughter that jumps. And the daughter becomes super shear, above the shear wave speed and above the Rayleigh wave speed, and propagates with something that's very close to the magic number that we saw was one of the branches of the Izmit earthquake. Again, this magic number, years later, of course, one can have been related to theory. Let me go back to the Izmit earthquake. You will say, well, you're a fraud, because this thing went two ways, but it didn't go symmetrically as you showed. It went faster this way than the other way. This became super shear, the other. Well, when I was visiting France about 6 years ago, I met Professor Le Pichon, who had just written a paper, and he had actually said that, well, the material to the bottom of this fault is different than the material to the top of this fault. And he has actually a lot of evidence regarding the geological evidence, and that this material has slightly smaller wave speeds than this one. So, okay, could that be the effect of the asymmetry? So we went back to the lab and took two different pieces of polymer. One was called polycarbonate. The other one was called homalite. There is a very small difference in wave speeds. This has slower wave speeds than this one. We oriented things as the 1999 Izmit earthquake. Actually, there is something called the positive direction now and the negative direction. And in the direction of sliding, parallel to the sliding of the slower wave speed material is the positive direction. Remember, this goes this way. The slower wave speed material goes this way. The other one goes this way. I'll call this, name calling, positive, and the other negative. And I'm going to actually explode the wire again and show you what happens. And if you squint, you will see that I have Mach cones here, but I don't have Mach cones here. So it really propagated with a super shear speed in this direction. Actually, it went up to a speed that was even close to the pressure wave speed of the slower of the two of the bimaterial interface. And here is a photograph of the shock waves that you see, but I have different materials, so they are not symmetric. You see, the angles are different, as you would expect. So really, what I'm saying happened in this bit is that part became super shear because of the bimaterial difference. Let me change gears a little bit and come to the work with Professor Lapusta and our common students. Seismology worries about whether these ruptures are crack-like or pulse-like. And I'll tell you what this is in a second. Really, imagine a carpet, and you are trying to move the carpet, and you are insisting, instead of actually going like this to the carpet and moving it, to move it without having any, producing any pulses to it or any waves to it. If you do move the carpet, you are producing a crack-like rupture because the whole thing slides. But if you produce a small bump and only one part slides, then you're producing pulse-like rupture. I will quantify that a little bit more. But really, what we wanted to see is, as we're sitting along the interface, how does the sliding happen microsecond per microsecond, actually nanosecond per nanosecond? So what we did is we devised a way with particle velocimeters to look on the top and the bottom of the fault and measure in real time with lasers, as this was spreading out, as these photographs were generated, the sliding speed of the top minus the sliding speed of the bottom, which gives you the relative sliding speed. So that's how it looks in the laboratory. In addition to the high-speed camera, you would have these local measurements. And these are happening above and below the hope. So you take the speed on the top minus the speed on the bottom, and you have the relative speed, the sliding speed. And if the sliding speed continues sliding, if this is the sliding front, say, along the interface, it continues sliding for a long way, and it does not heal again, then you have a crack-like rupture. If it goes up and down to zero again and locks again, and only this little part slides and moves, then you have a pulse-like rupture. Now, Professor Heaton here at Caltech, together with Professor Wirtman at Northwestern, has coined the phrase, really, pulse-like and crack-like. Wirtman was looking at bimaterials. Heaton was looking at single materials, the same material on top and the bottom. And they have different explanations regarding this phenomenon. And one explanation, when in the absence of bimaterial contrast, is what is called velocity weakening friction. That means that your frictional resistance when you are moving is less than your frictional resistance when you are static. So you probably, those of you that are skiers and you are in a very gradual slope and you are not moving very far, one way to actually move a little bit faster is to go like this, because you decrease your resistance and you start sliding better. So this is called velocity weakening friction, and this is what happens. And of course, I cannot explain the details. This is what generates pulses. But these have not been seen in the laboratory before, so Professor Lapusta and I started the program to look at the nature, the mode of rupture. Now, of course, in the computer, they have been generated for many years, but of course, models are models. Reality is a different thing. So here is a plot, for example. This is a case of an earthquake that is not super shear. It is, you see the shear front, and this is the result of a measurement that happened along the interface. And this is the sliding speed versus time in microseconds. And as you can see, nothing happens. The shear wave comes, and then suddenly there is an increase, a pulse increase of the sliding speed, and then it goes back almost to zero, and it heals. And this is the first evidence, experimental evidence, that actually these pulses do exist in a controlled laboratory setting. Now, you could actually superimpose this kind of thing on the picture that you get from the high-speed camera, and you see that really the way that this interface slides, it does not slide the whole way. It slides only as two pulses that are moving like this to the right and left, and they heal behind them. And this is actually a very important phenomenon in seismology because it explains a lot of things. As a matter of fact, if that did not happen, calculations will show that all the faults will melt because of excessive rubbing. But if the rubbing goes to zero, then you explain what is called the heat flow paradox in seismology. So, you can actually then show, again, with laboratory experiments, by changing the conditions, by going from an angle of 20 to 25 to 30, corresponding to these three cases. So shallow faults compared to the principal axis of compression. You can increase the angle and go from very narrow and very weak, sometimes even dying pulses, dying earthquakes, to stronger and wider pulses, and eventually to something that does not heal at all. So actually, you see here, there is a speed associated with the sliding here. It's not only the pulses to the right and left. The whole thing is unzipping. So the point is that you can identify the parameters that are responsible for this behavior. And then, of course, you can use the same technique to come back and look at the issue of transition from Subrayleigh to supershear by using these particle velocimeters. Remember, I told you about mothers and daughters, and I based that on photographs. But of course, it's much better to base them on measurements. So imagine what will happen if you are waiting at a point in the fault above and below to measure, and then the rupture is coming and you are capturing the behavior. And that's what you see here. As we kept increasing the angle or the driving stress, what would happen is that you will get cases like 30 degrees here, in which the sliding speed actually decreases substantially before the arrival of the shear wave, and it never heals. This is a crack-like rupture that is ready to transition from Subrayleigh to supershear. And at a later station, so this is measurement at 20 millimeters from the hypocenter, and this is measurement at 40 millimeters from the hypocenter. Further out, after the transition has happened, you see the clear formation of the daughter, which is in front of the shear wave. So you're waiting, you get the daughter first with the Mach cones, and then you see the remnants of the dying mother. Bad analogy. So, again, this is direct evidence that this mechanism that I was discussing indeed exists. But I like to show pictures always. So let me go back to the lab and show you some pictures and basically show you that the transition does not only involve crack-like ruptures transitioning from Subrayleigh to supershear, it may involve pulses that transition from Subrayleigh to supershear. So I'm going to explore again. You see actually the Mach cones, and if you squint your eyes, you see double Mach cones. And there is one line, there's another line. That means I have something which is a pulse propagating at speeds that are above the wave speed. Both tips move in a super shear fashion. So indeed, the existence of double Mach fronts proves the existence of pulses that are super shear. I don't want to elaborate too much on this point. It is important, though, because in order to persuade the seismologists that the super shear phenomenon is realistic for earthquakes, and since most of the earthquakes are pulse-like, it is important to demonstrate that pulses can become super shear. So here again is the direct evidence. We are waiting at a certain point. The daughter comes. It's a daughter pulse, not a daughter crack. The mother comes, is a mother pulse, not a daughter crack, because all of them go to 0, and then again to 0. So they lock, and behind them is the mother. And the shear wave has arrived at this point. Okay, I think it's time to go back to practical engineering considerations for a second. I told you, as a summary here, that small loads or angles give Subrayleigh ruptures and pulses. If you increase the driving force, you get super shear ruptures that are crack-like. And in the middle, you have all the combinations possible, and it can be done in a very controllable and repeatable fashion. There is also a speed of, there is a transition length very much like the earthquakes that we have seen. Finally, actually, if you go through the details of the analysis of the experiments and the analytical work, you can show that experiments support the presence of strong velocity weakening in these interfaces. However, what is the next step? We are interested in looking at the special ground-shaking signatures that is associated with these shock waves. You're going to be hit by these shock waves if you are a building close to the fault. What is going to happen to you? Is there a special signature? This is the work which is hot off the press that has been going on, and that's what I actually would like to concentrate on. Before I start, I would like to show you a video that was brought to my attention by my son. It's from Mythbusters. They actually wanted to show that shock waves have a structural effect. And they actually built this shack here, and they had a car. The shack had a window and a dummy inside it. It also had, they had glassware here, and they arranged for a supersonic aircraft to fly over in California. It was California, so you don't actually going to see the nice shock waves. It was not Florida like the other airplane, not humid enough. And they wanted to see whether the shock wave will break glass. So you don't see anything yet, but inside the shack, you see actually eventually the glass breaking. They had to bring the aeroplane down quite a lot to do it. Now, what is the equivalent question that I would like to answer? I would like to see what is the destructive effect of the shear Mach cone, not this Mach cone, on the buildings. So let me take you back to the Denali Alaska earthquake. And here we're lucky, because as I told you before, there was a station about 3 kilometers to the north called the pump station, pump 10 station. And it recorded these velocity signals. And the blue one is the fault parallel velocity. The red one is the fault normal velocity. As the earthquake was happening and was transitioning in that distance. That was a fluke. We don't have records like this every day. So Harsha and Mike came to me, and we discussed this, and we said, okay, these are interesting records. First of all, the things that are remarkable about them, the fault parallel, the shaking in that direction is much bigger than the fault normal. And that's exactly the opposite of what is happening with normal earthquakes. The other thing is that perhaps this is associated with the shock waves. We didn't know exactly. There is another signature following this, which is actually as ominous, and this looks very much like what happens in normal earthquakes, but of course it follows the first jump here. So the point was, there have been a few analytical studies on this effect, and I'm going to refer to them in a second, but nothing in the laboratory. So we actually set up to create these things in the laboratory. If you go back to theory, and I don't want to spend too much time on this, and you generate theoretical Subrayleigh cracks, shear cracks, and supershear with the Mach cones in the computer, and you put arrows here to represent the particle velocity because of these moving cracks, you will see actually the effect that was visible in the Alaska earthquake, because if you look at the arrows, in this case they are mostly vertical. The shaking is in this direction. In this case they are more horizontal. The shaking is in the horizontal direction. And this is really... so what we did is we went back to the laboratory and we put stations and measured both the fault parallel and the fault vertical. Again, this is the laboratory. You measure in this direction and in this direction. And let me show you the movies, because I think those are telling. On the left, I'm going to show you the Subrayleigh case. On the right, the supershear case. We are measuring at the same location equivalently. The red is the fault vertical. The blue is the fault parallel. And here are the two earthquakes happening. They're identical till one of them transitions. So here it happens. And in one case, you see a blip. The other one, it really goes to about 3 meters per second as the shock wave is coming to this location. And this is the big effect in the fault parallel that is associated with the arrival exactly of the shock wave. So this is the bad effect. And as I continue, and then it's interesting, so the daughter does this to us in the fault parallel direction, then the mother is coming in the back, and at this point the mother is being felt, and there is the effect of the mother, this effect. So here we have a 1-2 punch. First by the shock wave, and then by the dying mother. As predicted and as shown in the real records, this is much bigger than this, and actually things are reversed. In the Subrayleigh case, the red is bigger than the blue, whereas here the blue is bigger than the red. Okay. So now, of course, you can try and find features and differences and similarities between the natural record here and the record associated with the laboratory. And although they don't look identical because there are many differences in their cast with the laboratory, you can identify the features. Let me show you the similarity between A and A, a single pulse like this. In B, the red, you have the first effect of the coming shock wave, and then you have this curious feature, which is the effect of the mother, and this curious feature happens at about 37 microseconds, exactly when the mother is at the point of observation. Now, of course, that's not the only proof. One has to go to analysis and to computers to verify that what you say is correct. And here is the results of a simulation. Let me play it for you, which basically shows the whole effect. So this is a simulated earthquake that transitions to supershear. And you see the formation of the daughter from the mother. And it is this combination that gives the 1-2 punch here. When you're sitting here, the shock wave will process you first, but then the mother is still around when you are close to the transition. And this is the important and frightening effect. So I'm ready to conclude here, but I'm going to try and conclude with something that was only generated a week ago, actually less than a week ago. So this is where my colleague Swaminathan Krishnan comes into play. He's a civil engineer. He deals with buildings. He also has done end-to-end calculations from numerically generated earthquakes to the shaking of the buildings. So what he does is he looks at buildings like this, and this particular building is an existing building in Woodland Hills. I'm not going to give you the address. And it's a 20-story building. It was built according to the 82 code. And what we did is we took the laboratory records that we measured. We scaled them up appropriately with various scaling methods, basically comparing them in time and intensity to the Alaska earthquake. And we fed them into the building. So what Krishnan does is actually he builds finite, among other things, finite element calculations that calculate the damage as this building is shaken. And we had a shaking profile, so to speak. And we could subject this building to both the super shear and the Subrayleigh earthquakes. So imagine that you are in the same earthquake, and you have the Subrayleigh part and the super shear part of it. And the building is close to the fault. You have two different locations, identical building, close to the fault, one next to the Subrayleigh part and the other one next to the super shear. The question we asked, and I was very nervous because I had to give this lecture, and I didn't know the result before we shook the buildings, was which one will fall? So, by the way, if you look at the top view, this particular building that was built according to the 82 code, it features a symmetric placement of moment frames. That means, actually, those are the moment frames. This is a bad projection, but you see they're not symmetric in the cross-section of the building. So actually, the center of resistance, those are the stiffening elements. The center of resistance does not coincide with the center of mass where the forces really are assigned. So mass inertia is where the driving force is. The resistance is somewhere else. So there are torsions of the building. There is a cantilever arm. In new designs, that would not be the case. So let me show you what happened with this building. Identical building. One is fed the Subrayleigh, excuse me, I'm doing it the other way. The Subrayleigh is here. The super shear is here. You see cross sections, and you see a top view, the penthouse view. You're going to see the shaking of these buildings as the earthquake comes by it. Now let me orient you here, because this is important. The fault is running in this direction, along the y direction. Okay? And remember, for super shear earthquakes, the fault parallel is the big one. For Subrayleigh earthquake, the fault normal is the big one. But remember also that in the super shear earthquakes, I have a 1-2 punch. So let me run it for the first time. And time is running. This is coming up. And the shaking will be starting right now. Maybe. And the building is moving in the fault parallel direction. Look at what is happening to the penthouse. And then it's going to shake in the other direction. And as you can see, very fortuitously for my lecture, the super shear case collapsed. Now, it's interesting to understand why. Remember, that the codes, let me run it once more, the codes are such that damage is accumulated. If I shake a building, it damages the different elements, damage. They have a memory, they keep the damage. And when we have the 1-2 punch, the first one damages the elements, and normally they will not expect another arrival so soon. When you have the mother coming behind the daughter, moving in the other direction, that's what produces the collapse. It is the difference in quality of the signature that produces the collapse. And again, that does not happen in the Subrayleigh case, for which the poor building was actually designed. Of course, there is the new shape is a little bit on the skew side. But so let me run it once more. And I'm almost done. Is it running? No, now it's running. It may be interesting. You see, those are the offsets of the penthouse in one direction, in the other direction. And of course, these motions have been magnified by a factor of 5 so that you are able to see them properly. Remember, it moves in that direction, in this direction, and then it collapses. Now, there is a bit of good news. And the good news is that actually if you take the same kind of building, but retrofitted, this is redesigned, and according to the 97 code, and here you place the moment frames in the correct, in a way that the two centers coincide and you don't have too much torsional motion, and you do exactly the same thing, you do not get such catastrophic collapse. And I'm going to just show it to you and stop. It's running. Again, this is the super shear case. This is a Subrayleigh case. Again, we will move things mostly this way before anything happens to this one. And then it will move the other way. But because of the design of the building being improved, you're going to see that after a while, the two cases are looking very similar. The only difference being that after the total shaking is done, this one has permanent deformation. So, with this, I would like to finish my talk and basically tell you, I don't want to read these conclusions. I just want to tell you that we have been very excited about the discovery, the laboratory discovery of this phenomenon, and that has allowed us to actually interact with theoreticians and numerical analysts, and now with civil engineers to try and understand its importance when it happens. These are rare phenomena that actually will happen every perhaps hundreds of years, but they have happened along the San Andreas Fault. They have happened in the Western United States. As a matter of fact, out of the examples that I showed you, 3 out of 6, or 4 out of 6, were in the United States. They will not be happening every day, but if they do, they will happen in very straight parts of the San Andreas Fault that have not unlocked, they have not unzipped for a long time. I think we should be ready for them, and that's why we have been interested in actually speaking to civil engineers and doing this controlled laboratory experiments to see what is the hazard. Thank you very much for your attention.
This program is brought to you by Caltech. Visit us at caltech.edu.